From the lamp on your desk to, I don't know, the massive GO train, electricity is just everywhere. This invisible force powering, well, everything.
It really is. It's fundamental.
But it is invisible, right? So how often do we actually stop and think about how it, works? How do we even grasp something so vital?
That's a great question. It's this amazing flow of energy constantly transforming. You've got energy stored in a battery, say chemical energy.
Right.
Then it becomes electrical energy, making charges move, and then it turns into light or heat or motion. It's quite a journey.
Absolutely. And that journey, that's what we're getting into today. We're doing a deep dive into electric circuits. You've shared some really great material, and our mission here is to pull out the core ideas, give you a solid, intuitive feel for how things like current, voltage, and resistance work together.
And how they behave in different setups, different circuits.
Exactly. And even look at the power sources, the batteries themselves, because they're not always as simple as they seem. We want you to walk away with some real aha moments.
Yeah, the goal is a clear conceptual map, not just definitions, but understanding the relationships, how it all fits together.
Okay, let's start with the big three, the core concepts: current, voltage, and resistance. How should we think about current first?
Okay, current, think of it simply as the flow. It's the rate at which electric charge is moving. The classic analogy is water in a pipe.
Right, water flowing.
Exactly. Current is just how much water flows past a point each second. It's the rate of flow. We measure it in amperes, or amps, named after André-Marie Ampère.
Amps, okay.
So 1 ampere means 1 coulomb of charge, that's the unit of charge, is flowing past a point every second.
So it's about the quantity, the volume of flow per time. Now, something that always tripped me up a bit is this idea of conventional current, because the electrons, the actual charges moving in a wire, they go the other way, don't they?
Yes, that's a common point of confusion, and understandably so. You're absolutely right. In metal wires, it's the negatively charged electrons doing the moving, flowing from the negative terminal of the battery towards the positive. But historically, before electrons were fully understood, the convention was established that current flows from positive to negative.
Like a historical accident almost.
Sort of, yeah. And it just stuck. So all our circuit diagrams, all our standard rules use this conventional current direction, positive to negative. It doesn't change the physics or the calculations, just which way we draw the arrows.
Got it. And measuring this flow, that's an ammeter.
Correct. An ammeter measures current, and here's the crucial bit. You have to connect it in series with the part of the circuit you're measuring.
In series, okay. Why?
Because you want the current to flow through the meter. Ammeters are designed with extremely low resistance, so they don't really impede the flow they're trying to measure. The current just passes right through.
Makes sense. Okay, so that's the flow. What provides the push to get it flowing in the first place?
That's where potential difference or voltage comes in. If current is the water flow, voltage is like the water pressure.
Pressure difference, right?
Exactly. It's the difference in electrical potential energy between 2 points. It's the electrical push that motivates the charges to move. Technically, it's the work done or energy transferred per unit of charge.
So it's an energy driver behind the current, and the unit for that is the volt.
Yep, the volt, named after Alessandro Volta. 1 volt means 1 joule of energy is transferred for every coulomb of charge that moves between those 2 points. So you can also think of volts as joules per coulomb.
Okay. And measuring voltage, that's a voltmeter, and it connects differently.
Completely differently. You connect a voltmeter in parallel.
In parallel.
Yes, across the component or the 2 points where you want to measure the potential difference. Unlike an ammeter, a voltmeter is designed with a very, very high resistance.
High resistance, why is that?
So that very little current actually flows through the voltmeter itself. You want it to measure the pressure difference without diverting the flow, without becoming a significant path for the current. That ensures an accurate reading of the potential difference across the component.
Okay, so ammeter in series, low resistance. Voltmeter in parallel, high resistance. Got it. So I have the flow, current, and the push, voltage. What about things that get in the way?
Yes. The opposition. That's resistance, symbol R.
Resistance?
It's simply how much a material opposes the flow of electric charge. Back to the water pipe analogy. Resistance is like a narrow section or maybe some gunk inside the pipe, making it harder for the water to flow.
Makes sense. And we measure it in
Ohms. The unit is the ohm, and the symbol is the Greek letter omega.
Okay, ohms. And what determines how much resistance something has? Is it just the material?
The material is a big factor, definitely. Some materials like copper or gold are great conductors, very low resistance. Others, like nichrome wire used in toasters, have high resistance. That's how they generate heat.
Right.
But it's not just the material. 4 key things. First, the type of material, as we said. Second, the length of the conductor, longer wire, more resistance. Makes sense. The charge has further to travel through resisting material. Third, the thickness or cross-sectional area. Thicker wire means less resistance. It's like having a wider pipe or more lanes on a highway, easier flow.
Ah, counterintuitive maybe, but yeah, wider pipe, easier flow. Okay.
And fourth, temperature. For most conductors, especially metals, higher temperature means higher resistance. The atoms vibrate more, getting in the way of the electron flow.
Interesting. So material, length, thickness, temperature. Got it. Now, these 3 things, current, voltage, resistance, they're all tied together, aren't they? This brings us to Ohm's law.
Absolutely. Ohm's law is really the fundamental relationship between them, discovered by Georg Simon Ohm.
And what does it state, basically?
It states that the current flowing through a conductor is directly proportional to the potential difference, the voltage, across its ends.
Directly proportional. So more voltage means more current.
Exactly, provided that the temperature and other physical conditions stay constant. Resistance is the constant of proportionality here.
Okay, so mathematically.
The classic form is V equals IR. Voltage equals current times resistance.
V equals IR. Simple but powerful.
Incredibly powerful. It tells you if you double the voltage, you double the current if R stays the same. If you double the resistance, you have the current if V stays the same.
But you mentioned provided conditions remain constant. Does that mean it doesn't always apply perfectly?
That's a key point. Not everything obeys Ohm's law perfectly. Think about a regular incandescent light bulb filament. As current flows, it gets incredibly hot.
Yeah, it glows.
And as we just said, temperature affects resistance. So as the filament heats up, its resistance actually increases. This means the relationship between voltage and current isn't perfectly linear. We call materials like that non-ohmic. But for many basic circuit components at constant temperature, Ohm's law is an excellent approximation.
Okay, that makes sense. Non-ohmic. Good term to know. All right, so we have the building blocks. Now, how do we put resistors together? Let's talk about series and parallel circuits. What's the deal with series?
Resistors in series are connected one after another end to end. Imagine them forming a single chain. There's only one path for the current to take.
One path, like a single-lane road.
Exactly. And because there's only one path, the current has to be the same everywhere in that series circuit. Whatever current leaves the battery must flow through the first resistor, then the second, then the third. It doesn't split off anywhere.
Okay, same current everywhere. What about the voltage? Does it stay the same too?
No, that's where it gets different. In series, the voltage divides among the resistors. Each resistor takes a share of the total voltage provided by the source. Think of it like a voltage divider.
Voltage divider, okay.
The sum of the individual voltage drops across each resistor will add up to the total voltage from the battery. And importantly, the amount of voltage dropped across each resistor depends on its resistance. Bigger resistance gets a bigger share of the voltage drop.
So voltage splits, current stays the same. And how do we find the total resistance for resistors in series?
That's the easy part. You just add them up, R total R1 plus R2 plus R3 and so on. If you have a 10 ohm, a 20 ohm, and a 30 ohm resistor in series, the total resistance is simply 10 plus 20 plus 30 equals 60 ohms.
Nice and simple. Okay, practically speaking, what are the pros and cons of wiring things in series?
Well, simplicity is one thing. Sometimes sharing the voltage can be useful, maybe save energy in certain applications. But the huge disadvantage, the classic example being old-style Christmas tree lights.
Ah, yes, the bane of my existence. One bulb goes out.
And the whole string dies. Because it's a single path, if one component breaks or is removed, the circuit is broken and nothing works. Also, adding more resistors in series increases the total resistance.
Which means less current overall, right? VIR.
Exactly. More total resistance means less total current flowing from the battery for the same voltage.
Okay, that's series. Now, what about connecting things in parallel? How does that work?
Parallel is different. Resistors in parallel are connected across the same 2 points in the circuit. Imagine multiple lanes splitting off from a highway and then rejoining later. You're providing multiple paths for the current.
Multiple paths, so the current doesn't stay the same anymore.
Correct. The current splits when it reaches the parallel branches. Parallel circuits act as current dividers.
Current dividers this time.
The total current flowing into the parallel section divides itself among the available paths. Then the currents recombine on the other side. The sum of the currents in the individual branches equals the total current that entered.
Does it split equally?
Only if the resistances in each branch are identical. Usually it doesn't. The current favors the path of least resistance.
Ah, makes sense.
So the branch with the lowest resistance will get the most current. It's inversely proportional. If you have, say, a 3 ohm and a 6 ohm resistor in parallel, more current will flow through the 3 ohm path because it's easier.
Okay, so current splits, favoring lower resistance. What happens to the voltage in parallel? Does it split too?
No. And this is the other key difference from series. In a parallel arrangement, the voltage, the potential difference, is the same across all the components connected in parallel.
The same voltage across each branch.
Yes. If you connect several resistors in parallel to a 12-volt battery, each one of those resistors will have 12 volts across it.
Okay, that's a crucial distinction. Same voltage, splitting current. How about calculating the total resistance in parallel? It's not just adding them up, I assume.
Definitely not. It's a bit more involved. You have to work with reciprocals. The rule is 1 divided by the total resistance equals the sum of 1 divided by each individual resistance. So 1R total equals 1R1 plus 1R2 plus 1R3.
Right, the reciprocal formula. Is there a shortcut if there are only 2?
Yes, thankfully. For just 2 resistors in parallel, a very common scenario, you can use the product over sum rule. R total R1 E R2. R1 plus R2.
Product over sum. Okay, useful. And what's the overall effect on resistance when you add resistors in parallel?
This is interesting. Adding more paths in parallel actually decreases the total resistance of that section.
Decreases. So adding more resistors makes the total resistance less.
Correct. The total resistance of a parallel combination is always less than the smallest individual resistance in that combination. You're providing more ways for the current to flow, so the overall opposition goes down.
Wow, okay. That's quite counterintuitive, but really important. What are the practical advantages and disadvantages of parallel circuits?
The big advantage is independence. Each branch operates separately. If one component breaks, like a light bulb burns out, the other branches keep working.
Like the wiring in a house.
Exactly. That's why your whole house doesn't go dark if one bulb fails. Also, as we said, adding more parallel branches decreases total resistance, which allows more total current to be drawn from the source, which can be useful. The potential downside is that each component gets the full voltage, which might mean the circuit consumes more total power compared to a series arrangement with the same components.
Right, makes sense. Now, often circuits aren't purely series or purely parallel, right? They're combinations. How do we approach analyzing those?
Yeah, combination circuits are very common. The key is to simplify them step by step. Usually you start by finding the equivalent resistance of any parallel sections first.
Collapse the parallel part.
Exactly. Calculate the total resistance of just the parallel bit using the parallel rules. Then you can redraw the circuit mentally, replacing that whole parallel section with a single equivalent resistor.
Okay.
Now, that equivalent resistor will likely be in series with other components. So you then just add up all the series resistances, including your new equivalent one, to find the grand total resistance of the whole circuit.
Simplify parallel bits first, then treat the result as a series component. Got it.
Once you have the total resistance, you can usually find the total current using Ohm's law, a VIR, using the battery voltage and total resistance. Then you can work backwards, applying the series rules, same current, voltage splits, and parallel rules, same voltage current splits, to figure out the specifics for each individual component.
Let's maybe try a quick mental walkthrough. Say we have 2 6-ohm resistors in parallel, and that whole parallel pair is then connected in series with a single 4-ohm resistor. What's the total resistance the battery sees?
All right, first tackle the parallel part, 2 6-ohm resistors. Using the shortcut, our parallel exceeds 6. 6 plus 6, 5 plus 6 equals 36. 12 equals 3 ohms.
Okay, so the parallel bit is equivalent to 3 ohms.
Right. Now, that 3 ohm equivalent is in series with the 4 ohm resistor. Since they're in series, we just add them. 3 ohms plus 4 ohms equals 7 ohms.
So the total external resistance is 7 ohms.
Exactly.
That clicks nicely. But you mentioned earlier that power sources, like batteries, aren't always perfectly simple. There's something else going on inside them.
Yes, absolutely. In our ideal diagrams, we often draw a battery as just a source of pure voltage. But real batteries aren't perfect. They have their own built-in resistance.
Built-in resistance? Inside the battery itself?
Inside the battery itself, yes. Between its terminals. We call it internal resistance.
Yeah.
And usually give it the symbol lowercase r.
Little r.
Okay. And what does this internal resistance actually do? How does it affect things? Well, when current flows out of the battery and through the external circuit, it also has to flow through this internal resistance inside the battery.
Ah.
And whenever current flows through a resistance, there's a voltage drop, VIR, and energy is dissipated, usually as heat. So some of the battery's energy gets used up or wasted inside the battery itself, just overcoming its own internal resistance. This is why a battery can get warm when you use them heavily.
So some voltage is lost inside the battery.
Exactly. That's a great way to put it. We often call the voltage dropped across the internal resistance the lost volts. It means the voltage you actually measure across the battery terminals while it's powering a circuit is always a bit less than its theoretical maximum voltage.
Okay, lost volts due to internal resistance, sir. So there's the battery's theoretical maximum.
Right.
What's that called?
That's the electromotive force, or EMF, symbolized by the Greek letter epsilon, EMF.
Element epsilon.
Think of the EMF as the battery's ideal voltage, the total energy it can provide per unit of charge. It's the voltage you'd measure across the terminals if no current was flowing, like with an open circuit, just a voltmeter connected.
So EMF is the sticker price, the maximum potential. But what the circuit actually gets is different.
Right. What the external circuit actually gets is called the terminal potential difference, often written as VLOAD or V terminal. This is the voltage available to the load, the external resistors, when current is flowing.
And VLOAD is always less than EMF.
Always less, yeah, because you have to subtract the lost volts. The voltage dropped across the internal resistance R. That lost voltage is simply I times R, current times internal resistance.
So the total EMF is split between the useful voltage for the circuit, VLOAD, and the voltage lost inside the battery.
Precisely. That gives us the fundamental equation. The EMF equals the terminal voltage load plus the lost volts IR. So VLOAD plus R.
VLOAD plus R, okay.
And since VLOAD is the voltage across the external circuit, which has a total resistance, let's call rexternal, we know from Ohm's law that VLOAD I rexternal.
Right.
So we can substitute that into our equation. I equals I rexternal plus IR.
And you can factor out the current I.
Exactly, giving us I rexternal plus R. This version is super useful because it relates the battery's EMF directly to the total resistance of the entire circuit. The external part plus the internal part.
Occio I, rexternal plus R. That ties everything together nicely. So how does changing the external circuit, rexternal, affect the actual voltage the circuit gets? Load.
It have a direct impact, all linked through the current. Let's say you increase the external resistance, rexternal. Maybe you add more resistors in series.
Okay.
Looking at I, rexternal plus R, if rexternal goes up and I or R are constant for the battery, the total current I must go down.
Less current flows.
Right. Now think about the lost volts I. If I goes down, then IR, the lost volts, also goes down.
Less voltage is lost inside the battery.
Exactly. And since VLOAD plus R, if air is constant and IR decreases, then VLOAD, the terminal voltage available to the circuit, must increase.
Wow. So higher external resistance means less current, but a higher terminal voltage delivered by the battery.
Yes, closer to the battery's EMF. Now consider the opposite. You decrease the external resistance. Maybe you add more resistors in parallel.
Okay, lower external.
Lower external means the total current drawn from the battery will increase. More current flows.
Right.
Higher current means more lost volts, IR. More voltage is dropped across the internal resistance. So since I of load plus R, if R increases, VLOAD must decrease. The terminal voltage available to the external circuit goes down when the current draw is high.
That's fascinating. So the battery's output voltage isn't fixed. It actually sags a bit under heavy load. Low external resistance, high current.
Precisely. That voltage sag is a direct consequence of internal resistance.
What about the extreme case? A short circuit, where you just connect a wire across the terminals?
That's the danger zone. A short circuit means the external resistance, rexternal, is practically zero.
Okay.
According to I, rexternal plus R, if rexternal is almost zero, the only thing limiting the current is the battery's own internal resistance, R. Since R is usually quite small, the current I becomes extremely large.
Maximum possible current.
Maximum current, yes. And what happens to the terminal voltage? VLOAD. Since VLOAD IR rexternal, and rexternal is basically zero, VLOAD approaches zero.
So the external circuit gets almost no voltage?
Correct. Almost the entire EMF of the battery is dropped across its own internal resistance as lost volts, IR. All that energy is dissipated as heat inside the battery. That's why short circuits are dangerous. They can overheat wires, damage the battery very quickly, or even cause fires.
Definitely something to avoid. Okay, let's try putting some numbers to this internal resistance idea. Say a battery has an EMF of 4.5 volts and an internal resistance R of 0.5 ohms.
Okay, 4.5 VEMF, 0.5 internal resistance.
And we connect it to an external resistor, rexternal, of 14.5 ohms. What's the current and what's the actual terminal voltage load the resistor gets?
All right, first we need the total resistance of the whole circuit. Rho totally rexternal plus R equals 14.58 plus 0.5 each from 15 ohms.
Total resistance is 15 ohms.
Now we find the current using the EMF and total resistance. R total equals 4.5 V 15O. That comes out to 0.3 amperes.
Okay, current is 0.3A.
Now to find the terminal voltage, load the voltage across the external resistor. We use Ohm's law just for that part. The load to external equals 0.3A, 14.5.
0.3 times 14.5, that's 4.35 volts.
Exactly. So even though the battery's EMF is 4.5 V, the external circuit only gives 4.35 V because of the internal resistance.
And the difference? The lost volts.
The lost volts are internal HR plus 0.15 V lost volts adds up perfectly to the 4.5 V EMF. It all balances.
That makes it very concrete. Let's try one more that puts everything together series, parallel internal resistance. This sounds like a good challenge.
Okay, hit me.
Imagine a battery with an EMF of 9 volts. We don't know its internal resistance yet.
Okay. ABVR is unknown.
We connect it to an external circuit. This circuit has two 6-ohm resistors connected in parallel.
Two 6 ohms in parallel.
And that parallel pair is then connected in series with a 4-ohm resistor.
Okay, so parallel 6 is in series with a 4. Got it.
When we close the switch, we measure the total current flowing from the battery, and it's 600 milliamps.
600 milliamp, which is 0.6 amps.
Okay, the challenge. Find the total external resistance, external, and then find the battery's internal resistance.
Great problem. Let's do the external resistance first. We have the two 6-ohm resistors in parallel. Product over sum, 6 plus 6, 6 plus 6, 6 plus 6, 12 to 3 ohms.
Parallel part is 3 ohms equivalent.
Right. That 3 ohm equivalent is in series with the 4 ohm resistor. So external diesel plus 4, A is 7 ohms.
Okay, total external resistance is 7 ohms. Now for the internal resistance R, we know EMF equal 9V, current I equals 0.6A, and external equals 7A.
We use our main equation, A4 or I, external plus R.
Right.
Plug in the values, 9V equal 0.6A, 7 plus R.
Okay, how do we solve for R?
First, let's divide both sides by the current, 0.6A. 9V 0.6A equals 15. So the equation becomes 15 equals 7A plus R.
15 equals 7 plus R. Simple enough.
Now just subtract 7 from both sides. R is 0, 15, 7 is 8 ohms.
So the internal resistance of this battery is 8 ohms. That seems quite high.
It is relatively high for, say, a car battery, but not impossible for some types of batteries or perhaps an older degraded one. It makes the lost volts quite significant in this case.
Fascinating. That example really shows how knowing about internal resistance is crucial for understanding the real behavior of a circuit.
Absolutely. It completes the picture. You have the energy source with its own limitations interacting with the external load.
Well, we have certainly covered a lot of ground today. We've gone from the basics, current, voltage, resistance, through how they behave in series and parallel.
And tackle that often missed detail of internal resistance and EMF.
Exactly. We should now have a much clearer, more robust way to think about how electricity actually flows and behaves in circuits all around us.
It's hopefully demystified some of that invisible world, from the push of voltage to the pathways resistors create.
So the next time you flip a switch, charge your phone, or even just see those power lines overhead, maybe pause for a second, think about that invisible dance. The charge is flowing, the voltage driving them, the resistance shaping their path, even the internal struggle within the battery itself.
How might seeing those fundamental principles at play change how you look at the technology you use every day?
Or perhaps how might understanding them spark an idea for building something new yourself? That's something to think about.